Welcome to the seminar in cognitive informatics of the DIC-ISC-CRI and so forth here in Montreal. Je vais présenter notre conférencier, professeur Emmanuel DUPOUX, en français. I'm going to present in French first, and then I'll pass it to Professor DUPOUX, who will be speaking in English. So never fear. Professeur DUPOUX, d'abord, bienvenue à Montréal. Est-ce que je peux vous appeler Emmanuel après toutes ces ans?
Absolument.
OK. Emmanuel DUPOUX est professeur à l'École des Hautes Études en sciences sociales, EHESS, et il dirige aussi l'équipe Cognitive Machine Learning. C'est ça ce que vous l'appelez, Cognitive Machine Learning, au Laboratoire de Sciences Cognitives et Psycholinguistique, également EHESS. Il est aussi chercheur à IA et AI ou IA. Ses recherches portent sur les mécanismes de développement cognitif et linguistique chez les nourrissons. Donc, c'est pertinent ici. Évidemment, la psychologie expérimentale, l'imagerie cérébrale, l'apprentissage et l'informatique. Apprentissage automatique. Je ne parle pas où il détient des doctorats, etc. Mais je veux dire que son titre est vraiment plus facile de créer une IA enfant, une IA adulte. I presume that it's going to be addressing the views of Turing on this question as well. Am I wrong, Emmanuel?
No.
Good. So with that, I pass the parole to Emmanuel.
Okay.
The decision is that if you have important questions of comprehension, you can raise your hand here in the room. You can raise your hand or on the web. But we'll defer the substantive questions, the ones that will raise the hackles, for later. Donc, Emmanuel, le volant est à toi.
Merci beaucoup. Merci beaucoup pour cette invitation. Thanks for this invitation to this wonderful seminar series. I would like to start with a disclaimer. What I'm going to present is actually quite preliminary, at least in my view, even though I've been working on this for more than 10 years. The problem is difficult, but it's also quite interesting, so I'm not going to let it go. So as you actually guessed, my starting point here is this famous quotation of Alan Turing, which I think you all know. It dates back from the origin of both AI and cognitive science. At this time, I guess building an AI that would mimic the ability of human adults seemed quite difficult, apart from maybe even playing chess was not an easy one at this time. But because of also the very large number of tasks that an adult is able to do. So it probably seemed comparatively easier to build an AI that would mimic a much simpler organism, the human child, who basically has only one ability, the ability to learn. And then once you have built that, then you can educate the system as it would be a normal child. Now, today, the situation is quite different because we do have now AI systems that are quite successful in mimicking the abilities of human adults, more and more of them, to the extent that they are taken seriously as computational models of such abilities in a variety of domains such as language, vision, etc. So what can we do today with this proposition, this idea of Alan Turing? Uh, Now, it would seem that if we can do with current AI what was deemed very difficult at that time, which is like to mimic a lot of like human adult language, for instance, it would seem comparatively easier to model the child, and it would seem to be a piece of cake. What I'm going to try to argue during this talk is that it's absolutely not the case. Nothing could be more wrong than this idea that it's easier to model the baby than the adult. Okay, so here I'm going to concentrate on one particular aspect of this ability of human children to learn, that is their ability to learn their native language. Now, language is interesting in this context for at least three reasons. First, it's perhaps the most universally acquired skill across the globe. The vast majority of children, despite large variations in cultures, mode of education, family setting, etc., number of languages, acquire the language or languages spoken in their environment. Okay, and language acquisition even resists a variety of perceptual or cognitive deficits. Now, second, language is by far the most complex communication system ever documented in the animal world. The number of concepts and ideas we can express has been deemed to be virtually illimited. Maybe not illimited, but it's certainly of the order of magnitude of the number of atoms in the universe. Okay, so it's very, very much more complex than the communication systems in other animals. And third, languages themselves, they are very different from one another. Across cultures and historical times, they differ in the use of sound, gesture, words, the concept they express, etc., etc. So you cannot really say that it's just a question for maturation. Children really have to learn this ability, right? So this is a prime case of a complicated adult skill that is learned by the child. And it's also a skill that's now, today, is very well modeled by current AI system. So now let's have a look at how it could be acquired. Baby Lab, many years ago, I was actually interested in building an AI system that would learn like humans do. Jacques was not convinced by this project. In fact, he didn't like AI much. He said that if you want ever to build an AI system that mimics humans, what you have to do first is to study how humans work, and in particular, how they learn in the first place. And for me, it was a great surprise to discover that children learn language a lot faster than what we would think if we just observe how they talk, right? So if you take the vocalization during the first year of life, so this is like a timeline where in months, their output, their vocalization doesn't really strike us to be like extremely complicated linguistically or conceptually, right? But now, what was interesting in the lab of Jacques Peller and other labs around the world is that we can probe also the children comprehension. And what was discovered is that they make great progress in their ability to understand language way before they are able to express complex thoughts. So for instance, in this graph, each box here represents a different study and showing across different levels of linguistic structure from segments, prosody, word form, semantics. And you see that basically children learn to complex understanding skills of language at all these levels very early, much better, much earlier than when they talk. Like just to give an example, so at between 4 and 6 months, they start to grasp that the language around their environment has a particular set of consonants and vowels, and they start to specialize their perception on these consonants and vowels. Okay, but at the same time, they also become sensitive of the prosody of their language. They recognize a few words, they understand a few of them, etc. So that language acquisition starts very early. Okay. Now, what was puzzling to me, and is still puzzling to me today, is that the way in which children learn language is very different from how you would build a system that learns language, or how you'd imagine language can be learned by going to school. Like in school, you first learn the sounds, and then you learn some vocabulary, and then the grammar, okay? No, the children is very different. They seem to be learning everything at once. Okay, so they start to have before, for instance, if before even they have finished learning the consonants and vowels, they already recognize their name. Okay, and before they have a complete lexicon, they already start to understand that sentence is made of function and content words, for instance. Okay, so from a linguistic or even engineering point of view, this makes very little sense. I mean, how can they do that? And then it became worse. As I learned more and more about how children learn their language, it became more and more puzzling. So in the top graph here, you see in the y-axis, the estimated number of hours that children receive during 1 year. Okay, and in the x-axis here, you see you can't see because it's too small, but different studies across a large variety of languages that have been found in this. This is actually a very interesting paper by Alex Christia, who like collated all this data. And what you can see is that there's an extraordinary amount of variation in terms of the number of hours of speech that children receive across the world. It basically spans more than one order of magnitude. In some countries, children only hear like 70 hours of speech per year, and others it's about 1,000 or more. Now, what's even more surprising is that this variability of input is not accompanied by a similar variation in outcome. It's not the case that, for instance, children that are on the left have to wait to be 30 years old to reach the level of a 3-year-old on the right. That's not the case. Children seem to be learning roughly at the same pace, despite this enormous variation in input. And so basically, language acquisition is extremely robust to variation in input quantity. And this is already a red flag for the Turing hypothesis, especially if we consider that current AI models require even more input than that. So GPT-2, for instance, which is not a very good model at all, needs to accumulate something like 150 times more data than the children on the right, okay, which would correspond to experience of a 700-year-old child. And it gets worse for more advanced models. We'll come back to this question of robustness and speed of learning. Now, how do children do this? If we turn to theoretical accounts in psycholinguistics, we discover that cognitive scientists disagree widely about this. Actually, they disagree about everything. But so they even have different views about what the language competence is in the first place. Some researchers, for instance, propose that language is a kind of a formal system. Basically, infants would learn that through observation, observing these patterns of structure and then inferring the structures through some kind of inference process, which could be statistical or not statistical. Now, other scientists consider language to be primarily a mapping between form and meaning. And basically, children they learn a language by using co-occurrence of form and meaning as observed across these modalities. And a third group of researchers view language as a social construct, and basically children are learning through dense interactions with caretakers or peers. So this tripartition of theories is obviously a simplification. There are a lot more theories around. It's just like to give you some kind of overview of the state of affair. And in addition, there is a long-standing controversy about the mechanisms and source of information for language learning. So to be, again, extremely simplistic, you have nativists emphasize the role of pre-existing innate structure that guide language learning despite variation in input. And on the other side, empiricists emphasize the richness of the child environment and propose that basically this input and this richness is the driving force in the learning process. Well, we can cross these three different views of language and two extreme hypotheses about mechanisms. And you end up with like this, a table like this, where, for instance, on the language as structure view, you get nativists end up proposing theories like parameter setting, that the Chomsky proposition that you have an innate grammar and you only have to set a few parameters to converge on your language. And on the other extreme of that axis, statistical learning is actually one of the most current hypotheses about early language learning, is the idea that babies are just statisticians and they build a statistical model of the language by just observation. Okay. Now, this kind of, I'm not going to go through a table. Obviously, it gets complicated, but you can really see that there's a very large landscape of theories. Now, when I arrived in that field, I discovered all that. I found it was fascinating, but at the same time, it started to be a bit frustrating because after decades of work in the lab, basically this landscape hasn't changed. We still are having people who are in these different cells, and they don't seem to be moved by any kind of empirical results. So no matter what we find in the lab, there will still be people who are strongly proposing innate nativist views and language structure, and others say, no, it's a social construct. And so basically, we are still in a situation where none of these controversies can be resolved. So it's a strange situation for science, right? You never really, I mean, at some point, physicists decided, okay, Newtonian physics is less accurate than Einsteinian relativity. With some evidence, the people could agree with that. But in psychology, we seem to be stuck in these like endless debates. In addition, actually, none of these hypotheses can really address some of the puzzles I was mentioning before, that the fact that children seem to be learning at all levels at the same time, gradually across structures and in a very robust fashion. This is like difficult to explain in any account. Okay, so basically in brief, the more we discover about language acquisition empirically, the more puzzling it looks from a theoretical point of view. Language is a symbolic system, but it emerges from continuous sensory inputs. It's a hierarchical system, but learning proceeds basically disregarding completely the hierarchy. It's acquired with much less data than our best AI systems and despite large variation in input. So how is that possible? So this is where AI could be relevant. And here the idea is that would be to take Alan Turing's ideas and turn it on its head and say that in order to make progress in understanding how children learn, maybe it can be useful to try to build a computational system that actually try to reproduce this learning pattern given the same input. So this like reverse idea is not also a new idea. Since Turing's time, various scientists have tried to build formal theories of language learning, for instance, or computational systems that reproduce language learning pattern. And I must say that, I mean, despite the fantastic interest of this early literature, they didn't really succeed in building such a system. Now, maybe that's going to be the case for a long time, or maybe we can try it again. And what's new now is that first, we have a much better understanding of the sort of possible mechanisms from development science. Field linguistics has expanded enormously thanks to accumulation of data from wearables worn by children and then transcribed and put in repositories like ChildDesk, but now this is growing enormously. And then obviously also the AI has made a lot of progress. So now maybe we are in a better position to do this. What's interesting also is that current AI models come in different shapes, which can be roughly mapped to these different hypotheses of regarding what is language or what is the language faculty. So you have for language structure, you have basically what's called self-supervised learning systems that have been proposed, and they really map well on this idea. For language as map between form and meaning, you have multimodal learning AI systems. And for the interactive view, then you have a multi-agent reinforcement learning, which is a whole class of AI systems that can be leveraged. So we are now in a better position. What I'm going to do in this talk is really focus on this first hypothesis, because that's the one that's really widespread one, at least when it comes to the very first years of learning language. And also because it's the easiest one to test. So we're going to focus on this little corner of the grid So the empiricist view and the view that language is a structure, and so that comes to the what has been called the statistical learning hypothesis. So here I'm going to present one study that was the first attempt that we had with two great PhD students to address that with modern AI tools. So I will start to have first a word of method. So what we want is to simulate how infants learn a language. But typically people have been focusing on modeling the learning process, but that's not enough. What you really need to do is to build free models. You need to build, of course, a model of the learner, and that's what AI systems are good at. But then you also need to build a model of the environment. Okay, and by that I mean that basically the learner is taking its inputs from an environment, and so basically it's interacting with some kind of world, and so you need to do the same thing for the model. The model also needs to interact with some kind of world that will get its input from. So that's the model of the environment, and obviously if you want to have a good model, the model of the environment should be as close as the environment of the child. That's a super important point. Super important, but I'm going to come back to that, of course, throughout the presentation. Now, the third thing you need to do, obviously, is also to have a good model of the outcome measure, of the outcome of the learning process. And that's typically done, as I showed before, in the lab. You bring the baby in the lab and you make some measurements about using head turning, e.g., whatever, to evaluate the vocabulary, syntax, knowledge, etc. of the child. So we need to have exactly the same or as close as possible a procedure so that we can compare the two. Okay, so this is important to have. So again, not just one model. We need three models, and they need to be as close as possible as the child. Otherwise, we are not really doing something that will be useful for answering the questions. All right. So now, again, don't hesitate if you have clarification question at this point. I'm going to go through some technical details, and please interrupt if you have a problem with that. So, okay, so in this first study, we said, okay, so we're going to evaluate here the statistical learning hypothesis. The statistical learning hypothesis posits that the child is an observer and he's a statistician. So basically, he will be submitted to some kind of audio, right? Principally audio. If he's not a sign language learner, he will just learn principally from the acoustics. And so what we decided to do, for lack of a better idea, was to use audiobooks recordings. So we took audiobooks that were in French and English, and we varied the amount of speech to cover the whole range of the scale I showed before, between like children that have not a lot of speech to children that have a lot of speech, and to cover basically the equivalent of 3 years of life. Yeah, is there a question there? Okay, I thought I heard some noise. Okay, so basically, yeah, that's what I was saying. So we varying the amount between 50 hours and 3,000 hours, that's going to cover that. Now for the learner, okay, so that's sort of the interesting part, the modeling part, really. So we can start with basically this paper by Hellman in the 90s. I remember discussing that in the lab with Jack Miller, and at this time we were utterly unimpressed by this model, but I think we were wrong. But so anyway, so that's a model that has the following shape. You present the model in the original paper, characters, okay, text. So series of characters, and the model has some input units, a hidden unit, and output units. And the task of the model is to predict the next character. Okay, so you basically prepare your text and you train the model like this. So this basically, you can unfold that in time. So now you present this letter and you have to predict the next one. That letter you have to predict the next one. And these are the activations of the network. So that's a very simplified recurrent neural network. And at that time, what was found is that the system, you can look at the probability of the output letters, And what was observed by Hellman is that they seem to be able to learn word boundaries because the probability of each letter was decreasing within the word and then going up for each time you have a transition between words. Okay. So even though you present everything without word boundaries, the system is sort of be able to learn the segmentation implicitly. The other thing that was found in the paper is that if you inspect the hidden layers of these networks, you seem to be finding the system is learning some semantic representation. So the verbs were occupying different place in the model, in the states of the model than the nouns, etc., etc. So it was a sort of an interesting observation. We hated the paper because we thought, well, this is not much different than just doing a PCA over the distribution of the input, which is true, but still the model is basically that's what the model is learning. So, and the other thing that we didn't see at this time is that the model is actually a probabilistic model of the input. And the way you can see that is that, okay, you present the beginning of a word or a sentence, and then the output can be viewed as a probabilistic distribution of the possible continuations. So in this, if you start with this, it can continue with an O, with a space, or it is a very low probability to continue with a C because it actually is not a word. Okay, so more formally, what the system is really doing here is computing the probability of xt plus 1 condition on the past. So this is a condition probability. And when you make the product of all these conditional probability, you end up with the total probability of the sentence. So this model is learning a probabilistic model of sentences in English. So it is a probabilistic model. Okay, right. So what was also interesting, I'm just in passing, is that Hellman said in the paper, this simulation should not be taken as a model of word acquisition. And that's interesting because actually it was a model of word. But the reasoning of Hellman was that he had this idea that basically what listeners are doing when they are learning is not predicting the next thing. I mean, I think Hellman was intrinsically someone believing in the interactive, social, constructivist view of language. So he didn't believe in the statistical hypothesis himself. That's a sort of a funny thing. Okay, so let's go back to where we are now. So we have a model of the learner, but the problem is that it's taking text as input. And babies are not using text. They go to school. When they go to school, if they go to school, they already know the language, so that cannot be the way in which they learn the language. So what we wanted to do in this paper is to find a way to have a model like that, but works with raw audio. Okay. Now, basically, this is the problem I've been working on with machine learning colleagues for the past 10 years. Okay, so this is actually more complicated than it looks. And we can formulate this in the following way. Can we automatically discover some discrete units, linguistic units, perhaps like phonemes, consonants and vowels, from the audio, such that these units can then be fed to a language model that would learn like the Hellman system would do, okay? Yeah, by the way, sort of the recurrent network idea of Hellman is the basis of the GPT models. I mean, it's just the same idea. The models are bigger, architecture is a bit different, but the training, everything is the same. The conceptually is the same model. Okay, so this is a long story, but I'm going to summarize it by saying that a lot of people had actually also been working on this problem. How can you learn, can you find a representation of the audio that's good enough for making linguistic distinctions, okay? And so people have been working on this for many years, both from a computational neuroscience point of view, trying to model what the cochlea is doing and what the first stages of auditory cortex is doing, or from an engineering point of view. And so at this time, the models were really scattered. So what we tried to do with the first ERC I got like 10 years ago was to find a way to compare all these models. and actually also classify them. So basically, there are two kinds of ideas. How can you learn without any kind of supervision, just like as an observer, a good representation of the speech sounds by just listening, okay? And so one idea is that idea of a compression, of the compression. So if you look at the bit rate of the signal, it's quite high. So you can encode a speech signal around something like 2000, you can compress it 2000 bits per second. That's really, really compressed and not very good quality. But still, that's basically like a lot of bits per second. Now, if you take speech represented as a sequence of letters or phonemes, the bit rate is really a lot less. So roughly something like 70 bits per second. So the idea is that basically your representation of the audio as a sequence of phoneme is a task of compression. You remove a lot of information, you only keep the linguistic content. So people have been trying to do compressive algorithms using mixture of Gaussians or autoencoders with some kind of discrete code in between. So there's a whole class of algorithm that does that. And then there's a sort of a more recent class of algorithm that goes around the idea of prediction or predictive coding. And so here, the idea of predictive coding, which is explained here, is the following. You start with some kind of audio. Okay, so this is the audio representation. Then you transform that into some kind of abstract representation, like, for instance, not abstract, but more compact representation, like a spectrogram or some kind of representation. And then basically you try to use these different levels of representation to predict the future. So this part of the network only sees the beginning of an audio and tries to predict successive frames of the audio, but it's not really trying to predict the audio exactly. It's trying to just reconstruct this latent intermediate representation, okay, like a spectrogram. So this was called this quantitative predictive coding, and this looks really similar to the Hellman idea of predicting the future based on the past, but it's done in a continuous representation, continuous audio, not discrete units like text. But when you do that kind of task, then you basically end up with a representation that's actually quite good. So how can we know it's good? So what we did was to compare the different models using a discrimination task, which is basically what we do when we test babies. So when you want to probe whether babies have learned a particular contrast, you test them in a discrimination task. So for instance, you present Japanese babies and English babies with ra versus la. And so you discover that the English are very good at distinguishing ra and la, and the Japanese babies, after a certain age, they lose the possibility to distinguish ra and la, so they have collapsed the two categories. Okay, so this is IBX discrimination. Just to give you an idea, so this is if you start with a spectrogram and you do this ABX discrimination across all possible consonants and vowels in the language. So we do things quite systematically in machine learning. So we just don't do, in the baby's experiments, it's just one contrast, bar versus the ga. And in machine learning, you do all possible contrasts, so you have a more aggregate view. And so the performance of a representation like MFCC, which is roughly a spectrogram, is around 20% of errors. And over the years, the different models that have proposed these different ideas of learning representations have gotten better and better. And current models are below 4% or 3% error. And to give you like a representation of what that means is that when you have an ABX error in this kind of task of 20%, that's what basically you would get. So imagine that you don't have the colors between red and blue. You basically wouldn't be able to tell that you have two categories. But if you have an ABX of 5%, now you can see by the eye that you have two categories. Okay, so 4% or 3%, that's really very well separated, which means that these kind of models now are able to even though they are continuous representations, they are sort of able to segregate the different sounds in different clusters. Okay, so once you have done that, then basically the only thing you have to do to have discrete categories is just do the clustering. So now you apply a clustering algorithm like k-means, and now you have a set of discrete tokens. Okay. And yeah, so yeah, I'm going to skip that. But I want just to tell you a little bit of what these clusters look like. So these are things that are learned purely by listening to the speech. I give you recordings in English or in French for a certain number of hours, and then the system is discovering these units, and then these are like discrete units, okay? And now you can represent them in a heat map where you have the true phoneme labels. This is actually an English data set. And so this is on the y-axis, and on the x-axis, you have the label of these discrete units. So here we decided to make 50 units. So in English, in this representation, you only have like 43 or something. So you don't exactly have the same number of units and then phonemes, but you can see how they map with one another with a heat map here. So we can zoom on that, and we see that, for instance, the phoneme I has several clusters, several units have been dedicated to this one. Okay. Of course, it's all bottom up, right? The system is just making these clusters, has no idea what the phonemes are, but we can sort of interpret them as several different variants of E. If you look vertically, then you find that the same unit, for instance, unit 23, corresponds actually to several phonemes, not just to one. So the mapping is not perfect. The system is sort of cutting out the acoustic space into things that map roughly to phonemes, but not exactly to phonemes. It also dedicates some units to silence, because the system doesn't know what is silence and what is speech. It's just like discovering patterns in the audio. So since there are a lot of different background noise, you dedicate a lot of units to that. And now if you move to like 500 units, you have the same basic pattern. It doesn't really change. Okay, so you just have more units per phoneme. Okay. Now, once you have done that, you can now train a language model, a recurrent neural network, like in the Hellman case. But instead of having characters, now you have these like phonetic units that have been discovered. Okay, I don't want to call them phonemes because they are not phonemes. They are sort of pseudo phonemes or quasi phonemes. Okay, once you have done this, you train your language model, then you can actually analyze or also run experiments on your model using tests like lexical decision or syntactic acceptability judgment. And the way you do that is you basically present the audio of a real word like brick and a non-word like a blick. And because this model is producing a statistical, it's a statistical model, you can actually compute the probability that the model assigns to brick versus blick. And you'd expect, in fact, these experiments are also run in babies where you have a preference for, you measure the preference for baby for words versus non-words. And basically you'd count as a good classification if the probability that the model assigns to a real word is higher than probability of a non-word. And you can do the same thing with sentences that are grammatical or non-grammatical. Okay, it's the same idea. Language model is a probabilistic model, so we can extract the probability of the input. Okay, so that's how we test our models. Now, we did our cross-linguistic design. So as I said before, we had like cut the input into chunks of 50 hours, 100 hours, etc., up to 3,000 hours in both French and English. And then we train the models with these various amounts of data. And then we evaluate either in their native language or in their non-native language. Okay, exactly as we would do an experiment in baby. So these are the results of the models after being trained with various amounts of speech in either the native or non-native language. And I don't know what happened to this, but this is the phonetic score. So this is the ABX discrimination, either run in a native language or non-native language. And so the thing you can see here is that the performance, the discriminability of the phonemes is increasing if you have more speech. So models trained with little speech are not very good, but they are, if after 3 years of equivalent training, they have a better performance, okay, more than 80% performance. So that's one thing, and it's a gradual learning. So we basically reproduce the idea that children can learn gradually more and more accurate representation of phonemes, even though they're actually never really representing phonemes at all, right? They are using these units that are not phonetic. Now, the thing that's a bit weird, I'm going to go back to that, is that they're also learning for the non-native, okay, which is a bit strange, but the reassuring thing is that the performance is better in the native than non-native, which is what has been observed in babies and adults also. Okay, and then this graph here represents the lexical score. So this is like brick versus blick, okay? And the chance level is 50%, just like in the ABX case. And here you can see again that the performance is improving if you have more hours of speech, but it's not improving in the non-native case, which makes sense because the fact that if you learn the words of French, it doesn't make you better to discriminate, to recognize the words of English. Maybe there's a little bit of overlap in vocabulary that explains this tiny effect here, but that's really very small. Okay. All right, so here I'm going to skip that. Yeah, just to reinforce the view that I said before, that the units, the phonetic units that are learned, they are not phonemes. And the way we can view that is to measure the average duration. Okay, so average duration of phonemes is the green histogram. The average is around 70 milliseconds. And so you have some short phonemes, some long ones, but it's typically some kind of Gaussian like that. The distribution of duration of these pseudophonemes is completely different. It's more like an exponential. It's way shorter than the phonemes. And it doesn't get better. So if you get more and more training with the language, actually units become shorter and shorter. They don't converge to phonemes. So the models are not making better phonemes representation in the sense of closer to the linguistic ones, but they are better in their ability to discriminate, and they are better in the sense that they sustain lexical learning as well. All right. So here we try to see whether we could replicate the Hellman thing of indication of segmentation between words. Nothing at all. So it's even if you average across many trials, you may find some indication that there could be a drop in probability between word boundaries, but at the individual of single sentence, there is absolutely nothing. It's completely soaked in noise. So there is no indication that there is. So basically, these models are learning both lexical information and phonetic information without phonemes and without words. Okay, so linguistic units cannot be found, but we can find evidence of learning. So this is actually a different way to analyze the model. So we have these acoustic representations, the quantization, which is the pseudo phonemes, and then the LM. So another way, more qualitative to understand what's going on is to actually spy on the model by plugging electrodes, virtual electrodes, and having the system reconstruct what the system is thinking. So the way it's basically like the GPT thing. You prompt the model with some beginning of sentence, and then you let the model to continue the sentence, and you can hear what the system is thinking. Okay, so this is just an example here on things trained on audiobooks. So I hope you can hear it.
When an aristocracy carries on the public affairs, it's...
So this is the prompt. So you put this at the beginning, you prompt the system with that, and then the system is going to continue, right?
When an aristocracy carries on the public affairs, its verification there may be in science, the connections of the valley to which it was called upon to lecture, conferring on similar descriptions of opinion, and in other instances which appear to have never exceeded the same results. It cannot be found that the notion of the most ideal...
Okay, I'm stopping there because you can see, I mean, what you can hear there is that the system is able to reproduce English sounds and also English words and a little bit of syntax. It doesn't really mean anything. It looks like it really doesn't mean anything, but it's like there is some serious amount of language that's been learned by this system, right? Just by observation without any text. And if you train the same system on conversational speech, you get that.
Yeah, it's just totally. I guess what doing about life involved had man sergeanti the words.
Well, I'm talking in computer writing.
Yeah. Where are you calling from?
I'm calling from Quashina.
Oh, yeah, okay.
Yeah.
Okay.
Okay.
I used to schooled in the Middle East.
I'm from India.
Yeah. I used to have a fan all the time. What was your common American?
Okay, so I'm going to stop there. So this model has been trained on conversational speech. It's actually trained on binaural conversational speech. So you have two persons talking at the same time in the imagination of the model. So you can view that as a stereo model here. And you can see that the model is able to also to reproduce laughter and this kind of stuff. So these are also represented as discrete units because the system here is not text, it's not phonemes, it's quantized audio. And the system has learned that in quantized audio, in this situation, there are things that are laughter that can be reproduced. And so it's just reproducing that, okay? So the system is really learning the distribution of the input. Okay, yeah, I talked also about the sentences. So this is a test that has been devised to analyze whether language models are good at syntax. So it's based on minimal pairs of sentences. This one is acceptable, this one is not acceptable. So there's a long list. I'm not going to go there in detail, but basically the performance in syntax is not great. With 1,000 hours of audio, there is only 51% accuracy and the chance being 50%. So it's really close to chance. It gets better if you have more audio, which means that the system is also able to learn a little bit of syntax by this method of pure observation. All right, so conclusion from study one, a model based on statistical learning hypothesis fed on audio signal can actually learn phonetic contrasts. It can learn word forms, and it does not require any innate knowledge. It doesn't use any linguistic categories, and it's actually reproducing in parallel the gradual learning of both of all the levels. Okay, so this basically looks good, right? Now, so here we go to the second study where this sort of early success was qualified a little bit. Here in this second study, we revisited some of the finding of the first one with a sort of slightly more critical view. So first of all, as I said before, there is this problem that the system is learning also to discriminate phonemes that it hasn't seen. So the model is improving in English, even though it's presented with French. So this is actually never has been proposed. So this is a graphic proposed by DIC-ISC-CRIA on the possible theories of acquisition of phonetic contrast. And so some of theories propose that you start very high and you lose only the non-native contrasts. Or if you are perceptual learning, you start very low and you learn on the native contrast, but not on the native. But no one actually is proposing something like this. So this is like completely outside of the scope of any linguistic psycholinguistic theory. There's a second problem, and the second problem is that if you look at the x-axis here, so the curves, the learning curves for lexical scores seems to be reasonably linear, but the x-axis here is logarithmic. So that's really strange. That means that to get basically 10% better at recognizing words, you need to double your input size, which is strange. Now, okay, let's go back to the, so this is like, on this graph, you see the percentage of children that know a particular set of words of the CDI inventory as a function of age in month, okay? So in this one, you see also linear increase. And if you compare it with the models, they look similar. So you'd say this model is really a good model for the baby, except that again, the axis here is logarithmic and here the axis is linear. Also, the y-axis is not comparable. So what we did in this study here is that we tried to calibrate the two axes. So now we put, we sort of reconstruct the quantity of speech into a pseudo age in month. And we try to reproduce the same kind of task in both the model and the baby. And where we end up there now with something completely different. Now, the curves here are sort of, they are no longer linear. They are like basically logarithmic. And if you try to reconstruct the level of performance of the baby, it would take you a lot longer, like something like 500,000 years. So that doesn't look good, right? The third problem, or the second problem here, is that this kind of scale that we propose is good, but then babies are not really listening to audiobooks. They are listening to naturalistic speech. So here what we did was to take recordings of the children's input that is being done by field linguists, and we computed the signal to noise of the input they receive. So this is called the long form. Long form recordings are recordings for the whole day, okay? And then there's virtually no overlap between the signal to noise of the audiobooks and what they really hear. And also there's a lot of reverberation, which is because parents are not talking 2 centimeters from the ear of the children as people recording with their microphone. They are typically farther away, and that creates reverberation. Okay, this is just the signal problems. They're also talking less articulated than audiobooks. So what Marvin did was to set up a benchmark to compare the computational models between audiobooks and long-form recordings. And the short story is that, so this is the lexical learning curve, also still the logarithmic axis here of the audiobooks. And that's what you get with when you feed the model with realistic input. Basically, no learning, completely flat. Okay. So that's a big problem, right? Okay. So conclusion for this study is that, what we did in the first study was to simplify the model of the environment. And instead of using real audio, we use audiobooks. And the problem of that is that, so it provides a proof of concept that a learner, a statistical learner, can learn from audiobooks, but children are not learning for audiobooks, they're learning for ecological data. So now we are stuck, okay? So that really shows that if you don't use the right model of the environment, you are not solving the same problem as the child is solving. And so even if your model is correct, you can't prove that because it's actually not, actually the model is actually not able to reproduce the results if you are closer to the real input of the child. The other important lesson of this study is that it's really important to compare not only the shape of the curves, but also the calibration of the axis. X and Y should be made comparable. Otherwise, you think you have a model that explains something, but it's actually not working at all, or not working the same way. So basically, that's where we are at now. I'm just going to go quickly here because this is the work in progress part, where what we're trying to do now in the team, both at EHESS and also in my team, in my AI team at Meta, is to basically change the hypothesis about the learner. We started with this empiricist idea, and now we are investigating the nativist view. So the nativist view, the idea is that the system doesn't start from scratch. It has a lot of innate knowledge and constraints for the learning. So basically, yeah, so the same thing here. So basically, the neural networks I've been showing you are random networks, very generic. The same networks can be used for learning video and learning audio and speech and whatever. And so it's learning, but it's learning very slowly because it doesn't have any inductive bias. In contrast, children start with a brain that has been evolved for millions of years, that has been specialized to process speech and audio and language maybe in a particular way, and that's maybe why they are learning so fast. So basically, this is like the poverty of the stimulus again, right? So, but this time with quantitative data and not just like a principled idea. So what Maxime Pauly has starting to do in his PhD was to say, well, can we reproduce this evolution? Instead by starting with random network, we can start with networks that have been pre-trained with something. So in this study, he has pre-trained the language model with speech from a different set of languages. Okay, so you imagine that people have evolved to process language. So you take like 20 languages, and then you pre-train and you take that as the initial point of the learning at birth. children would have inherited from this like ability to learn in these 20 precursor languages, and now they start the curves look quite different. So instead of having this increase in performance for both native and non-native, you get something much flatter, still improving though for the native. He actually also did that by replacing the pre-training by just listening to non-speech sounds with actually quite similar curves.
Emmanuel, can I ask you one quick question? I was lost a couple of minutes ago when you said visual and audio. What does that, what do you mean?
Well, so the architecture of the neural networks, which is nowadays a transformer architecture, is basically the same architecture for everything. People have been using this kind of very generic type of architectures and neural networks, and they don't really change much when they use it to build a GPT model for text or a video understanding model. They're sort of very generic things, and that's the nice thing with. It's actually considered as a good thing from an AI engineering perspective, because you basically, the only thing you have to change is the training set, and the learning component remains the same.
But is there a homologue of this in another, exactly what you did, but in another modality?
Yeah, so I didn't prepare the slides here, but I have my colleagues. Actually, I've been working with a team of Yann Lequin, who is trying to learn what is called a word model based on video. So the idea is that you just have video and try to predict the future based on the past. And he's found that you can, if you feed the system with this thing, you can reproduce some of the intuitive physics results that have been observed by Lee Spelke, etc., etc. Now, what he's discovering now is that in order to get that, you need to train your model for equivalent of millions of years of video data. And that's basically the same problem we are having here.
Yeah, I understand. There.
The same amount of data of the child and also the same amount of noise that the child has, then they don't learn anything. So it's really like a half empty, half full glass. The animals are extremely good statistical learners, but the children are even better than that. And how are they so efficient at learning? That really is the question we are looking at now. So does that answer your question?
Yes, it resolves the uncertainty. I have more questions, of course.
Okay.
Go ahead.
Okay. So I'm going to wrap up because I would like to have more of these questions. So we are sort of one idea is to use training, basically use the same training system, but consider that there's a part that's evolution that starts before birth and throughout evolution. Okay, and so that the system doesn't start randomly; it starts with some kind of structure. And then you can see whether with this kind of pre-training, you can now reproduce more of the results of the child. So that's one idea we are pursuing. Then there is another idea that has been proposed by Marvin in his PhD, was to basically include new modules. So in the first, what we had was the contrastive predictive coding, learning pseudophonemes from raw audio. And what he showed is that if you present realistic audio, it actually doesn't learn anything. Basically, what it's learning is the statistical distribution of the noise. If you take the environment of the child, it's 90% or 80 or 90%, it's non-speech during a whole day, right? Speech is only a very infrequent event. So if you have a statistical learning model, it will learn the statistical distribution of the input. And if the input is in majority non-speech, it will learn non-speech. And so that's the problem with the statistical hypothesis in the first place, is that it's basically, it's just like too generic in a way. And so what Marvin did was to add modules that would filter the input and only retain the part that contains speech. So this is like, this module here is a voice activity detection. It's basically removing everything that's not speech. So if you have like 10 hours of audio and only 10 minutes of speech in that 10 hours, you only train on 10 minutes of speech and the rest you throw away. In fact, there is some evidence that children at birth are actually attracted, they look more towards the source of speech than the source of non-speech. So this kind of module could be considered as an innate bias that the student has to basically discard the non-speech and learn in priority the speech sound. So when you do that, you actually improve the performance, but that's not enough. And there are other modules. I don't have time to go into that, but you can start to add more and more like hypotheses about exactly what the system could start with initially to be able to learn language in a more efficient way. These two things are about actually a speaker. It's like when you have naturalistic audio, sequences of speech are very short and you very frequently change speaker. You have one speaker, one other speaker. And so the system is, the statistical learning system is trying to predict the change in speaker rather than predicting the content of the language. And that, so it's learning the speaker information, not the phoneme information. So if you add this kind of module that tracks who is speaking and when, then you again, you improve the performance, etc. So what he finds is that, okay, you start with a system that has no filter, just statistical learning. You learn nothing with long forms, and then you recover with these additional modules some performance. You are not as good as with audiobooks, but certainly you start to recover the native versus non-native difference that is documented in children. All right. And so this is where we are at. There are a lot of other hypotheses that could be added. Like, for instance, children are certainly not like passive. They can listen to different sounds sources. If they hear something and they don't know the sound, they can go closer. And so they can learn the source, active source separation, and basically what's called the scene analysis, auditory scene analysis, by just moving around in the environment. So this is like, for instance, a different source of innate bias, is that the babies have bodies, and so they can interact with the world in a way that our passive listener model could not, okay? Other hypothesis is that they can self-play with their vocal tract. They are born with this apparatus that help them to produce speech sounds. And now they know when they speak, they know exactly the gesture they are doing, so they can hear the outcome. And that can help them to build this inverse forward model that would learn probably much faster than the pure audio model. So I have a PhD student working on this. And then basically, all the other hypotheses that you could have is that your babies have cross-model information, they have social feedback. All of them can be added to the model if you put them with the right database and tools. So fortunately, people have been starting to gather cross-model recordings. So this is Mike Frank at Stanford has this baby view dataset where you have egocentric recordings of the baby. So you see what the baby is doing, you can hear what they are hearing, etc. And so that's the kind of data that can be used to test these new hypotheses. All right, so I guess I'm wrapping up here. So we started with this idea that babies have this ability to learn language. It yielded a number of puzzles. Learning is strangely gradual, overlapping, very robust, very efficient. We have all these controversies about how they can do that. And then basically with AI, we started to answer some of these questions. Like, if you believe that babies are doing statistical learning, that can explain some aspect, the aspect of graduality and overlapping of the different levels. That was accounted for by a pure statistical model. But then for the efficiency and robustness, then that's not enough. You need some innate biases in order to actually filter the noise and focus on the relevant linguistic information. And basically, yeah, it's just the beginning, right? We would like to further on to add more and more of the different hypotheses about how language can be learned by children. And so to go back to the original idea of that reverse engineering human learning is easier than than modeling the adult state. I think it's pretty apparent by now that actually the task is much more difficult than it looked at the time where Alan Turing proposed that. It actually seems to be easier to build the adult model than the baby model. But at the same time, I hope I have shown that they are useful tools. I mean, now the AI has provided enough of these tools, and there's enough like progress in experiments and field linguistics that we have some ways to make progress in this idea of modeling the baby, provided there is a sort of a careful methodological setup and also a strong collaboration between these different disciplines. I mean, I don't think psychology can do it alone, and AI alone is actually not really interested in doing that. So it's like really you need a strong collaboration to do that. And also it's a pretty exciting new area to engage in. So yeah, that's developmental AI. And yeah, thank you for your attention.
Thank you. I hope there will be instant questions as well. I'll just start it off as usual. Turing's remark in his 1950 was not about speech. It wasn't saying that it's easier to study speech acquisition, there's the phonemes in children than in adults. That's it's an interesting interpretation, but that's not what he was talking about. He was talking about language. And so the question I wanted to ask you is, how would you generalize from the tendencies that are coming out of these findings to Turing's original question? Adult language, not adult speech, but adult language versus.
Well, I mean, the language is learned by humans through sensory signals. That's how we learn language. I mean, you can learn the foreign language by going to school and going to a library, but that's not how humans typically learn language. They learn through either speech or sign inputs. So I don't think you can really ask the question, I mean, unless you are looking at how adults learn a new language without talking, just by basically learning Latin. But I think even there, the amount, if you just compare, you go back to the slide I was showing with the amount of text that you need to train something like a GPT model, it's still way, way more than even adults going to a library or learning Latin really require. Even if you forget this question of speech processing, we don't need a lot of input to learn a language, even as adults. And the models, the AI models lean a lot more.
There's a lot of work being done here locally and with collaborators on acquisition of language. I don't know if you know the work of Rushen Shi.
Mm-hmm. Yeah.
And the thought that comes up is, how would you apply to, or what would be the application of Turing's intuitive remark there to the work that's being done on tolerance principle?
On what principle? Sorry, I
tolerance principle at University of Pennsylvania. The idea that the fast learning of children is something much more general than the biological human species. That it's something that's true about learning mechanisms in general. It's from University of Pennsylvania.
Yeah, I'm not sure I get the reference, but I think in general, if you look at animals. Well, I mean, if you look at a lot of other abilities, like for instance, if you go to robotics, I mean, you could also look at learning of skills like walking or like manipulating objects. Actually, currently, AI systems are completely unable to do simple object manipulation. We don't have I mean, the only robots you see are robots that are teleoperated by humans. But the current systems can't really learn I mean, there have been progress in locomotion, but the fine manipulations of objects is still completely out of reach. And this is something that's learned very quickly by children. So I think in general, yes, the humans and also animals are learning way faster than the current systems. In fact, you can also say that even like AI systems, they don't really learn anything. I mean, if you take something even like a ChatGPT, a GPT system, once it's deployed, it doesn't learn, right? It's either it works for your application, you can talk to Claude or to ChatGPT and solve your case, or it doesn't. If it doesn't, you can't train it. You have to wait that humans, there's a huge amount of effort in training models, and it's not an automatic system. So it's not part of the competence of AI systems to learn anything, despite the fact that it's based on machine learning. But that kind of learning is not the same as the learning that's done in animals or humans. Our learning is autonomous. We don't need anybody to tell us what to do. We just learn autonomously in our environment, whereas the AI systems need a whole team of data scientists, data engineers that collect the data, clean the data, prepare the data. Okay, that's a completely different thing. Yeah.
I completely agree with you on that. In fact, one wonders with motor skills, sensory motor skills, one wonders about the big dissociation between the way that AI is being applied to language in particular, because language is so close to computation, or seems to be so close to computation. So would somebody say that robotics should be looking at the evolution of the sensory motor capacity that mammals have in order to inform their learning work on sensory motor capacities? Is there a direct application of what you've said about language and speech to other aspects of sensory motor robotics themselves?
Yeah, so I mean, I've been recently talking a lot with roboticists because they are a bit annoyed by, I would say, by the sort of the success and sort of predominance of language models as sort of the way to do AI, because they cannot do the same with robots, right? And the big difference is that for language, there's the internet, there are libraries. I mean, basically, so much resources that are there that you can use to train models for the equivalent of millions of years. You cannot train a robot with the equivalent of millions of years because the robot has to live in the real world. And so it would take millions of years. so that's much more difficult. So that's why, I mean, roboticists are very interested in this idea of autonomous learning and how you can basically put a lot of inductive biases in the system such that you don't need so many trial and errors breaking your robot to actually achieve something. And that's I mean, I think what could be basically, yeah, so it's actually tough to do. I mean, it has this thing of inducing inductive biases has been done successfully, I think, for walking and locomotion in robots by using simulators. So you basically train your models for equivalent of millions of years in the simulator. And then that gives you inductive biases such that if you put the robot in the real world, then it will now learn fast to adapt to the real world because it has been trained like that. So I have actually a sort of a schema here, which like summarize the thing. So typically that's the first line is the way in which things are done with language models like GPT. So you have this what's called pre-training, where you train the model to do next token prediction, and then you have a system that doesn't do much. But then you have some kind of tuning where that's very short actually compared to the massive amount of data that's used for pre-training, where you hope that you turn the system into some useful assistant by just giving it rewards, etc. So that's how GPT model is trained right now. And And now, in contrast, the way in which it's done in organisms is very different. You have two scales. You have the evolution scale and you have the developmental scale. And that's and during the evolutionary scale, you already have interactions and feedback, etc., going on. Not just at the last stage here, throughout, right? So it's a very different kind of setting, different way of building AI. That I think roboticists are sort of doing that already when they can, when they have good simulators. They can do that for locomotion. Unfortunately, to be able to do like fine skill, motor skills and manipulation of objects, it's a lot harder to get good simulators that simulate the real physical forces in realistic ways. And so right now they're a bit stuck. And I think that's why robots are going to have to wait for some time to reach the same level of performance as the other systems. Yeah.
Il y a ici ceux qui ont soumis des questions qui veulent poser. Vas-y.
Bonjour, je peux la poser en français?
Oui,
Oui, oui, bien sûr.
Bonjour, merci beaucoup.
Oui, mais est-ce que je peux conseiller, Emmanuel, qu'après la question posée, répète en anglais et répond en anglais?
OK.
Merci pour cette belle présentation. Comme vous l'avez dit, c'est préliminaire, même après 10 ans de recherche. J'avais des questions, en fait, j'en ai deux. La première, c'est sur les biais d'induction. Est-ce que vous avez des compléments de recherche à venir sur éventuellement des questions comme c'est quoi les biais d'induction que les modèles de langage actuels adultes devraient avoir pour réfléchir comme un enfant d'une manière spontanée?
Oui, alors ça c'est une question, merci beaucoup. Yeah, sorry, I will just like, do you have to reset the question or just...
Je peux la redire aussi.
Yeah, okay. Yeah, so the question is about what kind of inductive biases could be put into language models to reproduce the sort of a reasoning capability of children, right? And I think as for reasoning goes, I mean, you can see that current models are not very good at reasoning. They are not very good at intuitive reasoning. A lot of effort is being developed now to make them be able to reason like humans, and they still make like this. They can be very, very good at some like reasoning tasks or like the Olympiad in math, but they sort of make stupid mistakes, like logical mistakes. So there's something really missing in the models because babies are able to reason even before they speak, right? You have all these experiments showing by René Barrière-Jean and Liz Pelkey, Susan Carey, showing that babies are able to make like sort of reasoning inferences even in a non-verbal thing. You show them, I don't know, you put 3 balls in a cup and then you remove 1 ball. This is actually Karen Wynn's result. And then you show the results and babies expect 2. So they can do the subtraction completely mentally, completely before they learn language. So this like elementary intuitive reasoning capability is there and before language. And it's probably some of it is learned, but it's also possible that a lot of it is already in very strong inductive biases about the representation of the world and properties of the world, like things like objects don't disappear and they reappear. That's a strong inductive bias, right? They have some permanence. You don't have to learn that, it's actually built in. So if you have already a built-in object permanence bias, then addition and subtraction for small numbers will become like something very easy to get, right? So this is the kind of thing that also can be get through evolution, like having some very basic principles of conservation of objects and mass and energy or something is actually something that's useful to survive, but it's also useful to make reasoning, correct reasoning about causality and in the real world. And that's the kind of thing that could be built on. And it's absolutely not built in any of the current language models.
Une deuxième question.
Merci beaucoup. Ben justement, on parle.
Lève la main un peu pour que Emmanuel voit d'où ça vient.
Ça vient d'ici. Alors, vous mentionnez justement le mot raisonnement versus learning. Je me demandais, je sais que c'est très difficile de modéliser tout ce qui est complexe. Et en fait, dans le raisonnement, il y a aussi la mémoire, il y a aussi, vous parlez de word models, donc éventuellement une modélisation du monde dans du contexte, mais jusqu'à quel point on peut parler de raisonnement versus apprentissage quand c'est surtout basé sur la langue actuellement dans les recherches que vous présentez, à ma compréhension en tout cas?
Yeah, so the question is about whether the distinction between reasoning abilities and basically memorization of language patterns, right? So I think it's a real important issue because currently if you take GPT models or models like Claude, um, they if you don't train them on examples of reasoning patterns in language, they won't spontaneously be able to do that, right? So basically, they are just reproducing the patterns in the training set. And so a lot of effort in making the language models be able to reason is basically constructing training sets where you have, I mean, for instance, you scan all the math books, you scan all the scientific articles, which are supposed to illustrate examples of reasoning. And then you hope the system will memorize that and be able to generalize. So what language models are doing is that they're able to generalize. That's for sure. So they are not just like repeating exactly text to the patterns that they have learned. They are sort of they repeat abstract abstract things they have seen. But so the question really is whether reasoning is anything different from that. And again, given the fact that you can find elements of intuitive reasoning in babies before they learn language, or even animals that don't have language, you have all these demonstrations of like causal reasoning on problem solving of birds or chimpanzees without any language. So I think if you view it in this way, like at least intuitive reasoning doesn't really need language at all, but it needs to have some grounding with understanding of the physical world. And basically the physical world is a causal system that's consistent, logically consistent. Okay? If there's one thing that world is, it's logically consistent. You have a cause consequences. It's like, okay, if you have a text, there's nothing in the text that makes it consistent. You can have like text is basically literature. It's basically narrations, and you can tell stories that are inconsistent. There's no problem with that. There's a lot of inconsistent discourse out there in politics, in everything. So people don't really care that much about that. So it's difficult to take the text to learn consistent reasoning from text. It's a lot easier from the world. But that's the current systems are not learning from the world.
We're running out of time, but I still want to encourage, for example, Jean-Louis de Sales, ça fait longtemps que je t'ai pas vu ici. Est-ce que tu as des commentaires ou d'autres in English or in French before I close?
Oui, merci beaucoup pour l'exposé. Bonjour Emmanuel et
Bonjour.
merci Étienne. Oui, j'avais une question sur l'idée que l'étude numéro, je ne sais plus laquelle c'était, l'étude numéro 2, étudiait le fait que le pré-entraînement soit de même nature que l'apprentissage lui-même. Et ce que je comprends de la troisième démarche, c'est de dire que non, il n'y a pas nécessairement d'adéquation entre ce dont l'apprentissage qui serait lié à l'évolution d'une part et l'apprentissage de l'enfant ontogénétique ne serait pas de même nature. Donc moi je trouve ça très intéressant et voilà, j'avais d'autres idées, mais vraiment si tu pouvais commenter là-dessus, de dire que c'est qualitativement différent. C'est-à-dire que l'apprentissage phylogénétique donne des mécanismes et après, l'apprentissage utilise ces mécanismes et il n'y a aucune raison, contrairement à l'approche empiriste, de penser que c'est la même chose.
It's going to seem strange to you, Emmanuel, to translate in order to answer. But these are recorded, and many people who can't come at exactly this time consulted after. So could you please?
Yeah.
Do you want me to say it in English?
No, it's okay. Emmanuel can repeat it in short.
Yeah. Yeah. So it's a very deep question, but the sort of the core of what I understood is that is there like so basically from a machine, I'm just going to say it in my own words, right? So from a machine learning perspective, there is no real difference between development and evolution. Everything is about some kind of optimization algorithm, right? So from a machine learning computational perspective, you could say that these two things are the same. Now, if you have the and the question is whether it makes sense to view that or to consider that they are really completely different processes. Certainly, from a biological perspective and a psychological perspective, they are completely different. Of course, for a baby, evolution doesn't have any causal impact, but the evolution gives them an initial point. So the baby starts with an initial wiring of the brain and also a body, and both having evolved through time, and that's this like embodied system that is going to learn in a developmental framework. From an evolutionary point of view, what's going on is like you have generations of babies that learn and grow and reproduce, etc. So it looks like a completely different. But I think from a computational perspective, these two things are a little bit interchangeable. So the way we can view that is that in organisms that are in a very stable environment, a very predictable environment, you can basically transfer properties of the environment into the genome, into the brain, and our organisms are very, very adapted. They don't need a lot of learning. They can work from the very beginning. They can construct their whatever they are. If they are spiders, they can construct all their traps and stuff like that without any learning. They don't need learning. It's completely transferred through the genome. And in other cases where the environment is more complicated, you don't have enough space to store everything in your genome, and so you sort of devolve the learning phase in the development. So you could view basically sort of that as a trade-off between storing in the genome, doing some learning during evolution, or doing some learning during the development, and you can sort of trade one for the other. But certainly at the level of mechanisms, biological and cognitive mechanisms, they are completely different. Yeah.
Okay, thank you very much. It remains only for me to thank you profusely for after all the tension about whether you were coming, it was all worth it. It was all worth it. And maybe I would close with a remark that this analogy between evolution and or phylogenetic effects and ontogenetic effects certainly has a lot in it, and many people made it in many different contexts. But one problem for the modeler, and you showed it with the robotic case, is that in order to do this by simulation, you have to simulate everything in advance. You have to. I think you have to almost understand the answer to the question you're trying to answer in advance in order to do it that way.
Yeah, that's true. I mean, and that's maybe the sort of maybe one of the limits of AI is that if you really want to have intelligence, you need to simulate the whole world, right?
Yes, but let's
which
not
also, which is impossible.
Don't forget Turing. I mean, the reason he said this analogy was not really because he was thinking that if you're doing evolutionary robotics, you should. I think he was taking language for the peculiar thing that it really is. When we talk about numbers of years and number of atoms, etc., with language, you can say in words everything that you're hoping to come out of all of this science eventually. That's how powerful a thing it is. Robotics isn't like that. It's the repertoire of all possible movements, maybe in a really philosophical sense,
right.
Stretch it and say, language is after all movements, and therefore it's robotics. But I don't think that's very serious.
Okay, yeah, I agree with that.
Okay, well, anyway, thank you ever so much. For this to have been as it deserved to be, it would have had to be a series of about 4 or 5 talks and not just one.
Okay.
So, but it was excellent in any case, and I want to thank you very, very much, and we all do, actually.
Thank you so much. It was a pleasure.